Hello, this is Paul from First Attack. In this video, let's prove Theorem 3.2.5, which is the triangle inequality in n-space. We just generate the triangle inequality in two space in R2 or R3 to n-space. Okay. I think you are familiar with the triangle, right? So if I draw a triangle, the sum of two sides should be greater than or no more, no less than or greater than the third side. Okay, this is triangle inequality. So here similar. See, I draw a graph. Okay, so you see clearly. But here the result is in space, okay, general n space. The first we call the triangle inequality for vectors. The second similar is triangle inequality for distance. So what is the first? Let me just draw a graph here first. U, V, U plus V, so we can, so A is similar like this. If this is a U, vector U, I draw another vector, this is a V, and then I link the beginning to the end. I should find the sum, right? Okay, so this is the sum of U plus V. Okay, can you see? So we do have this triangle. If this is in two space, it's quite easy to see the norm. Can you see? And this size, therefore, the length of this size, the length should be the norm of U, right? And the length or the distance of this side should be the norm of V. Okay, see the last, the third side. So this should be the norm of U plus V. Okay, so easy to see the sum of the U, the sum of the norm should be greater than or no less than, in case they overlap. Okay, if they cannot form a triangle, they overlap. In that case, they're equal. Otherwise, the sum of the sum of two sides should be greater than the third side. This is A. But in n space, we have to pay up to prove. Okay, and then B. What is B? B is just like this. Triangle is the distance. So, and this time let's see the vector as a point in space. A point. Okay, remember the same. So let me say here is the point. I just ignore the origin. From the origin to the terminal point, we form a vector, right? What I draw is just the terminal point. If this is corresponding to the terminal point of U, and the U to V, if I say this point is the terminal point of vector V, and that this is the terminal point of vector W, can you see? Therefore, if you link this, and the link this is not should be a right triangle. Okay, then link this. So we have a definition. So this is the distance. See, and that the definition between these two vectors, between the terminal points of two vectors, we define as the distance. So the length, okay, of this side should be the distance of U and the W, right? Okay, so this side from W to U should be the distance of W and to V, W and V. So from U to V, the distance we call it, the distance of U to V. Can you see? If we put this side and this side, okay, the sum of two sides should be greater than the third side. So it's the same triangle, right? So that's for B. But this is not a proof. This is only, or you say this is a proof for a triangle in two space on a plane. Okay, but now it's in space. So let's prove. Yeah, in space. So proof A. For A, we just do calculation. So let me start from here. I directly work on the norm of the sum. The norm of the sum is not easy to work on. Let me square first. Is that okay? So let's square. So this should be u plus v as a vector dot the vector itself. Okay, the first step. Okay, and then I distribute. Then distribute. After distributed, we should get what? We should get u dot u. Let me put it the first for you. The first what we use is the norm of w squared equals the vector dot times itself. Okay, we repeatedly use this result. So now I will distribute the first term and then the last term, the out v is 4 here. Okay, the out, which is u dot v. Put this, and then the in, which is v dot v dot v dot u, and then the last is v dot v, right? So plus v dot v, 4 terms, and then again use this same. Okay, so u dot u equals vector dot itself equals the square of the norm. Okay, so equals the square of the norm, and then the second 2 terms are the same because commutative. Okay, so symmetry. So therefore is 2 times u dot v. They are the same. And then the last, of course, is the norm squared. And then Cauchy-Schwarz. Okay, so the previous theorem we proved. For this, we can control. This should be less than or equal to. Okay, so this should be less than or equal to. The first I will not change. The second is 2 times the norm of u, the norm of v. Can you see? Okay, this is a Cauchy-Schwarz inequality. Okay, we learned in the previous theorem. Therefore, and then plus v squared, almost, and this is a perfect square. So we made this is a perfect square, which is this one plus this one, and then squared, perfect square. Okay, see what do we get? We get the sum, we get the square less than the square. Okay, we take square root. Therefore, so we take square root, which is the first u plus v should be no more than, less than, or equal to the square of this is this one. Let's take square root. Okay. You take square root, you will find this because both are positive, okay, and non-negative, so you don't need to put the negative there. Okay, so this is the proof for A, and then we look at the proof for B. Okay, remember dB is like this. The distance from a point to a point should be less than the distance from a point to the midpoint, and then from the midpoint to the last point. Should be right. Excuse me. The proof for B. Proof for B, we only need the results we proved in A. Use the definition, so I directed the distance from the beginning to the end. What is the definition? The definition, this is the definition. The definition. Should it be the distance between these two vectors, which is the distance, right, of the vector. The subtraction, okay, the distance. This is the definition. We need to put one more vector W or the middle point in. So we do this small trick. I put a small trick minus W and then plus W and then minus. See, we did not change anything. And then we associate. I put this together. I put this together. So we have the first distance, we see one vector. The second is another vector. So therefore, the first vector, we can see this is a vector and this is another vector. Okay. So we use the first triangle inequality we just proved. See here. Okay. So this is the norm of the sum should be no more than the sum of the norm. Therefore, this should be less than or equal to the sum of the norm. The first is this one. The second is W to B. Okay, so this is just we proved the result on A. Then by the definition, this is just the distance between U to W, the first. Second is the distance from the middle point W to the last B. See, this is the proof. Okay. That's all. Thank you.